All right, y'all, let's do this. All right, yeah, so what we're going to do is we're going to pick up where we left off last time talking about acids and bases. And really what we're going to focus on right now are these conjugate pairs. All right, remember we said that an acid will donate a proton and become a conjugate base. All right, and our example was we took nitric acid, HNO3, and we showed that when this donated a proton, it became the nitrate ion. All right, and if we look at what we had to do in order to get that formula, what did we do to the number of hydrogens? We decreased our number of hydrogens by 1, and also we decreased the charge by 1. Okay, so we're going to apply this same logic to a few different acids, and y'all are going to give me the formula for their conjugate base. All right, so to get your formula right, you're going to take away a hydrogen, decrease that net charge by 1. All right, so then HClO4, perchloric acid, is going to lose its hydrogen, so it's just going to be ClO4. Then I'm going to decrease that charge, giving it that -1 charge. Hydrogen sulfate is playing the role of an acid. That means it's going to lose its proton and become just a sulfate ion. Its charge was already -1, so when I take another one away, I'm at a charge of -2. All right, and then water is going to lose one of those 2 hydrogens, so become OH minus. Or we can write this HO minus. Either one works. You'll see either one. This one has a special name. Does anybody know the name of this ion? Hydroxide. All right, and just to kind of pause and make note that this is, again, kind of a way that we're updating the way that we're thinking about acids and bases. They're not just like chemical classifications, but they're the role that's played in a reaction. You know, nitric acid, if you spill that on yourselves, you want to take care of that immediately, right? That is a strong acid. It will burn like crazy. You wash it off. If we spill water on our hands, what are we going to do? Wash it off with more water? We're not concerned about it, right? Water isn't something that we would classify as an acid, but it can certainly play the role of an acid in a chemical reaction when it donates a proton and becomes this hydroxide ion. All right, so again, these are sort of roles that these molecules are playing in a reaction. Okay, so in each of these here, that donatable proton was easy to spy because it was listed first in our formula. Well, actually, it was easy to spy because that was the only choice, right? There are other molecules out there, specifically organic acids. All right, which contain multiple hydrogens. First of all, does anybody know what element is like featured heavily in organic chemistry? Carbon, right? It's all about carbon. And specifically, an organic acid or an organic molecule in general necessarily contains carbons and hydrogens. All right, so an example of an organic acid would be something like CH3COOH. And now we have multiple groups of hydrogens in our formula, and so the question is, well, which one are we going to take away in order to make our conjugate base? All right, so that donatable proton is always listed either first in your formula or last. You'll never touch the ones in the very middle of the chemical formula. Okay, so when I do my conjugate base here, I'm going to leave that CH3 alone, and I'm going to take away the one on the very end there. Okay, so if we're predicting the product of what happens after an acid donates a proton in a chemical reaction, we're going to take that acid formula and we're going to decrease the number of hydrogens by 1, and we're going to decrease the charge by 1. All right, we want to be able to play the same game with bases. Bases were our proton acceptors. And when they accept protons, they become the conjugate acid. All right, so let's take a look at a few bases here. What about the fluoride ion or the carbonate ion? Oh, well, let's do the one together first. Okay. So first of all, if we're going to do the formula for our conjugate acid, we need to do the exact opposite of what we did to do the formula before. Now we're going to increase our number of hydrogens by 1, and we're going to increase the charge by 1. So when fluoride accepts a proton, it becomes HF, and that charge will increase from -1 to 0. All right, so then 2 more examples here. Using this same logic, tell me what the conjugate acid is of the carbonate ion and water. All right, so we increase our number of hydrogens by 1. So now we got CO3. And what's my new charge? Just -1. All right, water we saw can play the role of the acid in a chemical reaction. It can also play the role of a base in a chemical reaction. It can accept a proton. In that case, I'm going to increase my number of hydrogens by 1. So now I'm H3O. And I'm going to increase that charge, so my net charge would be +1. Okay? Much like the hydroxide ion, this thing also has a special fancy name. This is what's called the hydronium ion. All right, and it plays a really important role in acid-base chemistry. Man, are we going to say the word hydronium so much today. All right, so this is another one that's going to be very important in our discussion of acids and bases. Okay, much like before, we can have our organic bases. And so let me give you an example here. CH3 NH2. All right, again, now we have like multiple groups of hydrogens. Where are we supposed to be adding to? These organic bases always have a very similar structural feature, which is that nitrogen atom. All right, nitrogen, it just turns out, it plays the role of a base very often. So we're going to add to the nitrogen. All right, when we're going and adding our number of hydrogens, increasing our number of hydrogens by 1 and increasing our charge by 1, where do we put those hydrogens? We're going to add it to that nitrogen. And we can note that it'll always be listed either first or last as well. Okay, so if I'm going to do my conjugate acid formula here, again, I'm not going to touch the CH3. That's just going to stay CH3. But I'm going to make this NH3 plus. Okay? And this isn't something that I expect you guys to have memorized. This is just kind of a fun fact. This is what you'll go way more into in organic chemistry. But if we looked at the structure of these molecules, you could understand why we add it to the nitrogen. All right, in my base, my nitrogen has this lone pair. All right, when it is literally that lone pair that is reaching out and grabbing that proton. So this would be the structure of my conjugate acid here. So, all right, there's a reason why we list it next to the nitrogen in the formula, and that's because that hydrogen is literally bound to that nitrogen in our molecule. All right, anyway, fun fact, bottom line, add it to the nitrogen. It'll either be at the end of the formula or at the beginning. All right, cool. So then let's just kind of put this into practice in, a little bit more practical of a manner here. How about y'all write me the balanced chemical equation for if we take hydroiodic acid and react it with ammonia. And I'm going to tell you the hydroiodic acid is the acid and the ammonia is the base, right? You're going to give me my two products, the conjugate acid and the conjugate base. All right, if I want my conjugate acid, which one of these am I going to look at, the acid or the base? The base. So my conjugate acid, I'm going to increase my number of hydrogens by 1, so we'll have NH4, and increase my charge by 1. My acid is then going to tell me what the formula of my conjugate base is. I'm going to decrease the number of hydrogens by 1 and decrease that charge by 1. Okay, so we're going to be studying a lot of acid-base reactions in this chapter. There's one that's going to play kind of a really prominent role, and that is what's called the autoionization reaction. Okay, so this is taking place in every aqueous solution. Anytime you have a bunch of water molecules, including in my water bottle right now, including all of your beverages right now, this reaction is always taking place between two water molecules. They're going to collide, and one of them is going to play the role of the acid, and the other is going to play the role of the base. All right, so just like before, you're going to tell me our conjugate pairs here. My conjugate acid and my conjugate base. All right, if you get, again, if you remember, we had special names for these guys. My conjugate acid would be what? All right, so if we take that base and we give it, it has to increase in number of hydrogens. So now we're H3O plus, this was that hydronium ion. And if we take our acid and we take away a hydrogen and decrease its charge, we get our other special one, hydroxide. All right, so in every aqueous sample that you have, water molecules are colliding with one another and forming into hydronium ions and hydroxide ions. All right. This reaction, we're going to talk about its equilibrium here. So we're going to give it that equilibrium arrows, those double-headed equilibrium arrows. And we're going to talk about its equilibrium constant, K. This reaction is so special that we give K a special little sign here. We call this KW, specific to the autoionization reaction. All right, and considering that both of those products, hydroxide and hydronium, would be considered aqueous, everybody take a second and give me the expression for KW, like we learned how to do in our equilibriums chapter, right? What am I talking about there? The what over what? Products over reactants business, yeah. All right, so I'm going to look at this balanced chemical equation. Products over reactants here, except what up there is not going to appear in my equilibrium expression? My liquids, right? So my equilibrium expression here will just be the product of the concentration of hydronium times the concentration of hydroxide. Products over reactants, but the reactants aren't there at all, right? Because they're both liquids. And just like any equilibrium constant, we can go and we can look up in a book what it is. And for this reaction, it is 10 to the negative 14. All right, now, something important about that 10 to the 14, which is a total lie, but it's going to make our lives a lot easier, is we're going to consider this to be an exact number, 10 to the negative 14. All right. Truthfully, it's not. It's got sig figs associated with it. But man, is that going to make life so much easier, so we're going to roll with that. Okay? And importantly, what this is really saying, and the important thing to keep in mind, is this means that in any aqueous solution, if you know the concentration of one of these two, so let's say hydronium, then you also know the concentration of hydroxide, and vice versa. In every aqueous solution, the product of those two concentrations have to equal that magic number, 10 to the negative 14. So if at any point you know what one of them is, you can figure out what the other one is as well, right? They're always linked together. Cool, so let's practice that then, all right? Let's say that we have a solution that has a concentration of hydronium equal to 0.025 molar. And we want to know what is the concentration of hydroxide. All right, so everybody using that auto-ionization relationship, take a second and tell me what that concentration of hydroxide should be. All right, so I took that auto-ionization relationship, the product of those two concentrations equals 10 to the negative 14, and I rearranged that equation to solve for my concentration of hydroxide. So now I'm going to take 10 to the negative 14 and divide by that 0.025. All right, my calculator spits out 4 times 10 to the negative 13. All right, if I'm doing sig figs, how many should I have? 2, so 4.0. And my units here for my concentration would be molarity. Okay, I guess we should go back up and be good. This 10 to the 14 does technically have units. You'll see that for whatever reason, with equilibrium constants especially, we're real lazy. The units here would be molar squared, because each one of these quantities are in molar. But again, anytime we're talking in concentration in brackets here, you can assume we're talking in molarity. Okay. The other thing that we want to note here, we got this really tiny number when we solved that problem. Let's look at this chemical equation real quick. It has this equilibrium constant where the value is 10 to the negative 14. What does that mean about this reaction? Does it favor the products or the reactants? Favors the reactants. And does it strongly favor the reactants or weakly favor the reactants? Very strongly favors the reactants, right? So this reaction is always going on. It's going to be really, really important, but it's only going on to a super teeny tiny amount at any one given time, okay? All right, so next thing, we're going to introduce formally here something I think everybody's heard of before, but maybe just haven't discussed sort of quantitatively yet, and that is the concept of pH. This is going to play a really important role in our discussion of acids or bases. I mean, the punchline is like 90% of the time from here on out, the name of the game is, what's the pH of that solution? All right? So the pH, importantly, it is the exact same information as the concentration of the hydronium ions, just on what's called a log scale. All right, but that's all it really is a reformatting of that same information. What's the hydronium ion concentration? When we're asking about pH, that's what we're interested in, hydronium ion concentration. All right, so our pH is equal to the negative log of that hydronium ion concentration. All right, so as you can see, as long as you know that hydronium ion concentration, you can find your pH. And actually vice versa as well. We could take the inverse of this relationship here, solve it for concentration of H3O+. And I know y'all are masters with your log algebra, but just to kind of formalize it here, this would be the concentration of hydronium is 10 to the negative pH. All right, so kind of like our autoionization relationship. If you know one of these, you know the other one as well. They are intricately linked together here. All right, so given our formula, let's just go back to that same solution. Right? We asked what is the concentration of hydronium ion? Hydroxide ion. And now we're going to ask, what is the pH? All right, so pH is the negative log of the concentration of hydronium. So we're going to find that log button on our calculator, do negative log, punch in that 0.025. Okay, we find that our pH is equal to 1.602059. All right. So we always got these three steps, right? Punch it into your calculator. Units, all right? pH is a weird one. pH is a unitless quantity. There are no units associated with pH, unlike concentration and just about everything else we've been talking about. Okay, and what's that last step that it's everybody's absolute favorite because this is a chemistry class? Sig figs. All right, well, wonderful. Y'all are in for a treat here. You know how we have different rules for addition and subtraction than we do for multiplication and division, right? That's because in the wonderful world of math, those are considered to be two different operations. They have like a theoretical difference to them. Well, congratulations, you have now been introduced to a third operation here, logarithms, which mean that we have a third set of sig fig rules that we're going to have to follow here. All right, it's really not too bad. But nonetheless, pH sig figs. All right, so the number of significant figures in your concentration, that is going to be equal to the number of decimal places in your pH. All right, so similar to multiplication, you're going to be counting sig figs in one of your inputs. All right, in your input, your only input. But this is not going to correspond to the number of sig figs in your answer. It is going to correspond to the number of decimal places. All right, so everybody take a second. Using that logic, round our pH here to the correct number of significant figures. Really the correct number of decimal places. All right, 2 sig figs in that concentration. That means 2 decimal places in our pH here. So 1.60. Cool. All right. So just to take a second to talk about this log scale business, why would they bother to put pH on a log scale? We all know the log is the button in our calculator, but there's kind of a reason why they do it. All right, and that is because in solutions, this concentration of hydronium will differ by several orders of magnitude. All right, by orders of magnitude, I mean anywhere from a concentration of 10 to the negative 1 molar, 10 to the negative 2, 10 to the negative 3, 10 to the negative 4, etc., etc. All right? And if you put that on a log scale, these orders of magnitude differences correspond to just differences of 1. So the pH of a solution that is 10 to the negative 1 molar is 1. 10 to the negative 2 is 2. 3, 4, 5, 6, 7. So it's this linear scale when your concentration is differing over huge orders of magnitude, right? A concentration of 10 to the negative 7 is way more dilute than a concentration of 10 to the negative 1. Nonetheless, a lot of the world around us is very sensitive to even little differences in hydronium concentration. I mean, your human body goes through great lengths to keep in a very narrow range of pH, right? So the bottom line is we see these quantities differing by huge orders of magnitude. That log scale is convenient for that. And I know everybody's like, I love algebra, log algebra especially, so this sounds super convenient. But yes, there is a logic behind why they do it. Cool. All right. So we're going to, now that we just defined pH here, we're going to revisit that auto-ionization relationship. And we're going to put that on that same log scale. Okay, so by that I mean we're going to take that auto-ionization relationship, which is again hydronium times hydroxide, gives you that 10 to the negative 14 value, that Kw. All right, and for fun, we're going to take the negative log of both sides. All right, we're just going to take this equation and start doing some algebra to it. All right, well, we got the negative log of hydronium times hydroxide equals the negative log of 10 to the negative 14. Okay, well, 10 to the negative 14 is just a number, right? So the negative log of 10 to the negative 14 is just some number. All right, so let's punch it into our calculator. Negative log 10 to the negative 14. What do we get? 14. Cool, so this side simplifies to just that simple number 14. Okay, and then looking on the left side, we're going to take advantage of some weird log algebra here. It turns out that the log of A times B is the same thing as the log of A plus the log of B. So we're going to use that to split up that product that's inside those parentheses. So the negative log of the hydronium ion concentration plus the negative log of the hydroxide ion concentration equals that number 14. All right, negative log of hydronium plus negative log of hydroxide. Well, we got a fancy name for one of these two, right? What do we call the negative log of the hydronium ion concentration? The pH. So this thing here is just our pH. And so the negative log of the hydroxide ion concentration we're going to call the pOH. Okay, in fact, you'll see this little p quite often in chemistry. That little p means the negative log of something. So anyways, this auto-ionization relationship, if we put it on a log scale, we get that the pH plus the pOH is equal to that number 14. Cool. All right. So, what we're going to do is now look at a type of reaction that we're going to be studying, what's called the acid dissociation reaction. Okay. The acid dissociation reaction is when we take an acid and we add it to water. The acid is going to play the role of the acid, which means that water is going to be playing the role of the base. All right, so again, let's practice our balancing of these acid-base reactions. We're going to pick hydrochloric acid as our acid. Again, if we're talking about an acid dissociation reaction, our other reactant is always water. Okay. All right, so my conjugate base, I'm going to look at what formula, my acid or my base, to get my conjugate base. Acid. I'm going to decrease my number of hydrogens by 1. Decrease my charge by 1. That gives me that chloride ion. In order to get my conjugate acid, I look at my base formula here. And because that base is water, what is my conjugate acid? Hydronium. I'm increasing my hydrogens by 1, increasing the charge by 1. All right. So in these acid dissociation reactions, we're always talking about adding acid to water, right? So we're preparing a solution of this acid where we take some from the back and we put it in some water. And what's going to happen is it's going to dissociate into its conjugate base. But because it's reacting with water, we'll always get that same second product, the hydronium ion. All right, and again, what we're concerned with is finding the pH of these solutions. So if I'm worried about the pH, I'm going to be looking at the concentration of which one of these products up here? Hydronium. All right, so here's the name of the game. In this acid dissociation reaction, we want to know how much hydronium ion is formed, because that will allow us to calculate the pH of that solution. Okay? So we got a lot of different acids out there. Importantly, we're going to divide the world of acids up into 2 buckets. Okay, we're going to cover the easier bucket first, which is our strong acids. Okay. Strong acids are called strong acids. Oh, wait. First, we got to do one more thing. Sorry. Back up top, we got a fancy symbol for the equilibrium constant of these reactions, kind of like we do Kw for our autoionization reaction. These ones we call Ka for acid dissociation reactions. Sorry, okay, now we can resume. So, strong acids, they have very large Ka values. All right, hydrochloric acid, for example, that Ka value is something like 10 to the positive 10. All right, so then what would we say about this reaction for hydrochloric acid? Does it favor the products or the reactants? Products. And does it strongly favor the products or weakly favor the products? Strongly. So this reaction right here, we wouldn't even bother writing this equilibrium arrow because we don't think about it as this dynamic equilibrium. We think about it as going in one direction only, right? Every bit of that HCl you put into that solution is going to dissociate into chloride ions and hydronium ions. All right, so they're very large Ka values, so they strongly favor the products. All right, so for strong acids, we're going to say that this acid dissociation reaction goes 100% to completion. Right? So again, what does that mean? That means every single molecule of HCl that you put in there is going to dissociate into chloride ions and hydronium ions. All right? That's going to make calculating the pH of these solutions, or rather calculating the concentration of hydronium ions, a lot easier because it simply means that the concentration of that strong acid that we start out with, right, that initial concentration is equal to the concentration of hydronium ions once this reaction has reached equilibrium.
And this is the case for all strong acids?
For all strong acids. All right, and I'm going to tell you right now that HCl is a strong acid, and you're just going to trust me, and I'll tell you how I know that here in a second. All right? So for right now, HCl is a strong acid. What it means to be a strong acid is that when you put it into water, 100% of those HCl molecules dissociate into its conjugate base and hydronium ions, which means that if we want to figure out how much hydronium ion we have, we just look at our initial concentration of that strong acid. Okay? So now y'all are going to take a second, and you're going to calculate the pH of a solution of hydrochloric acid, where that concentration of hydrochloric acid is 4.7 times 10 to the negative 3 molar.
You said the concentration of the strong acid is equal to
The concentration of the hydronium ions, because that reaction goes 100% to completion. All right, so pH, we need that pH formula. Tells me that my pH is equal to the negative log of the concentration of hydronium ions. And because HCl is a strong acid, that means that the concentration of HCl is simply equal to the concentration of hydronium ions. All right, so that means to get my pH, I'm just going to take the negative log of that concentration because this are both equal to 4.7 times 10 to the negative 3 molar. All right, so my calculator spits out 2.322, oh, nope, 3.2790. What are my units? Trick question. Yeah, we don't have units for pH. And how am I going to round my pH? 2 decimal places, right? Because I got 2 sig figs up here in my concentration. So I need 2 decimal places for my pH. So 2.33, no units. Boom. All right, so we're going to talk a lot about acids, and we're going to talk a lot about what the pH of a solution of those acids are. We're talking about this acid dissociation reaction here, where we're adding acid to water to form the conjugate base and the hydronium ion. It's always going to be the hydronium ion that's formed because we're reacting it with water, and that's the concentration that we're after in these problems here when we're trying to find pH. We talked first about strong acids. They have very large Ka values, so we get to say that this reaction goes 100% to completion, which means that if we know how much acid we started with, we know how much hydronium ion is going to form. All right, so you just trusted me that HCl was a strong acid. How did I know? All right, kind of a good news, bad news thing. Because there are a list of 6 strong acids that we just got to know. All right, so not a ton of them, but nonetheless kind of a pain in the butt that we got to have memorized. These are our 6 strong acids. All right, so first of all, 3 of them look a lot like HCl. They're both hydrogen paired with one of those larger halogens, so chlorine, bromine, or iodine. All right, notably, which halogen is missing from this list here are most electronegative? Fluorine. So HF, hydrofluoric acid, is an acid. It's just not a strong acid. It turns out that fluorine is just too dang electronegative and holds on to that hydrogen too well. All right, but all these other ones are strong acids. This is hydrochloric acid, hydrobromic acid, and hydroiodic acid. All right, the other 3 are when we pair hydrogen with one of our super soluble polyatomic ions. So for example, HNO3, nitric acid, H2SO4, sulfuric acid, and HClO4, what's called perchloric acid. All right, so these are these 6 strong acids. This list we just got to know. All right, so a few of your homework problems are dedicated to helping you memorize your strong acids. Kind of the intention is that you just do them over and over again until you get them all ingrained in your brain. If not on this list, we would classify that as a weak acid. All right, and we will get to weak acids next week.
because those anions are the most soluble?
It's because, yeah, they're super stable without that hydrogen. Perfectly happy to give it up. They're cool on their own. All right, so like I said, we'll talk about weak acids next week, next lecture. Now we're going to talk about kind of analogous to our acid dissociation reactions, which we use to study acids. We can also talk about base dissociation reactions. All right, this is when we take some base and put it in water. In this case, water will be acting as our acid. So let's just do an example here. Try to think of one we haven't done before. Let's do the phosphate ion. That's going to be our base. And again, your second reactant, always water, playing the role of the acid here. So everybody take a second. Give me the conjugate pairs. Complete this chemical equation for me. Okay, so if I'm going to do my formula for my conjugate acid, I'm going to look at my base. I'm going to increase the number of hydrogens by 1 and increase that charge by 1. If I do the formula for my conjugate base, I'm going to look at my acid. And this is another one that we have a fancy name for. What's my conjugate base? Hydroxide. All right, so in our base dissociation reactions, we always get some conjugate acid. That'll depend on what base we use. But then we always get the hydroxide ion. Okay, so now in direct analogy, so first of all, we again have our equilibrium constant for these reactions. And since they're base dissociation reactions, we're going to subscript them with a little b. All right, and in direct analogy to our strong acids, we also have what we call strong bases. Strong bases have very large Kb values. Which again just means that they're reactions that strongly favor the products. All right, so strongly in fact that we say that those dissociation reactions go 100% to completion. Okay, which again means that we get to say that the concentration of our strong base that we start out with initially is equal to the concentration of hydroxide when that dissociation reaction reaches equilibrium. Okay, so hopefully we can see kind of directly analogous to what we had just talked about with our strong acids. The thing about strong bases is, at least for our purposes, they're way easier to spy. These are just any soluble hydroxide salts. So any salt, any ionic compound that contains hydroxide that is soluble in water is a strong base. Okay, and so we've sort of heard of a bunch of these examples before: sodium hydroxide, potassium hydroxide, lithium hydroxide, right? Those metal ions paired with hydroxide would all be strong bases. Okay, so let's see if we can't figure out the pH of a solution. All right, what is the pH of a solution with a concentration of sodium hydroxide equal to 0.075 molar? 0.753 molar. All right, given everything that we've discussed today, I want you to see if you can't figure out how we would go about getting the pH of this solution. You don't, because again, you're going to assume the reaction goes 100% to completion, meaning that the concentration of hydroxide is just simply going to be equal to the concentration of strong base. Okay, so look, we're like, okay, fine, we need a pH here. Well, I know my pH equals the negative log of the concentration of hydronium. All right, and I was paying attention, so I know NaOH is one of those strong bases, which just simply means that the concentration of that strong base is equal to the concentration of hydroxide. All right, But I'm not quite there yet because my pH is in concentration of hydronium. I have concentration of hydroxide. How am I going to square these two away?
Calculate the pOH and then subtract by 14.
Yeah, so that's one way, right? The other way, both ways are our auto-ionization relationship, right? So what we need is now that KW equilibrium that locks together the concentration of hydroxide and hydronium. And absolutely, you could use the normal concentration form or our log form here, whichever one you're going to find to be more convenient. I really like this one, but whatever. I'm going to use the other one just for the sake of, I don't know, because I'm willing to. All right? Really, because you're going to see me use the other one a lot more. So just to do this one real quick, again, we're going to now need to use that auto-ionization relationship. The concentration of hydronium times the concentration of hydroxide equals that 10 to the negative 14. All right, so we're going to have to use all three of these here in order to get the pH of the solution. Again, I'm going to give you a minute or two to see if you can't get there if you have not already. All right, so if I have my concentration of hydroxide, I can use that here in my auto-ionization relationship. So I'm going to rearrange to solve for hydronium. I get 10 to the negative 14 over that 0.0753. Gives me a concentration of hydronium equal to 1.328 times 10 to the negative 13. That's a concentration, so I'm going to give it units of molarity. I'm also going to note that this number would have 3 significant figures associated with it. And now I get to use my pH formula. pH is the negative log of that hydronium ion concentration. So I'm going to do the negative log of that value. I get 12.8767.9. Okay, and if I'm going to be good and round this to the, right, no units, right? And if I'm going to be good and round this to the correct number of sig figs, really I'm going to pay attention to the number of significant figures in my input, and that's going to correspond to the number of decimal places in my pH. So my pH of this solution is 12.877. Okay, so if we have a solution of strong base, That means that this base dissociation reaction goes all the way to completion, which means that the concentration of that strong base is simply equal to the concentration of hydroxide. But if I want the pH, I'm going to have to use my auto-ionization relationship, in order to convert from concentration of hydroxide to concentration of hydronium. All right. So last thing to note real quick, when we did our strong acid, we got this really low number for our pH. When we did our strong base, we got a bigger number for our pH. All right. So we have these classifications for pH ranges. If you have a pH lower than 7, that is considered to be an acidic solution. All right, and looking at our auto-ionization relationship, you can convince yourself that that means that the concentration of hydronium is greater than the concentration of hydroxide. If we have a pH greater than 7, we call that a basic solution. All right, that means that there's more hydroxide than there is hydronium. Concentration of hydroxide is greater than that of hydronium. And lastly, if your pH happens to fall exactly on that 7, we call that solution neutral, which means that the concentration of hydronium is equal to the concentration of hydroxide. Cool. So when we put our strong acid into water, what happens to our pH? It falls into which range? A pH of 2.33. That would be acidic. And that checks out, hopefully, because we put a strong acid in there. All right. And likewise, if instead we check our pH of our strong base, that 12.877, we would consider that a basic solution. Cool. Wonderful. All right, we will pick up with this next week, talking about our weak acids and weak bases.